All right. Thank you for that introduction. Um, and certainly thank you to NREC for inviting me to share some highlights of our research, most of which is in NREC funded or associated with NREC funded outcomes. I want to first just thank NREC for their commitment annually to funding nutrient research and funding research that strengthens the idea of sustainably producing goods. It's well needed. As you see on the screen, this is a rainfall event, about 2.5 inches, that occurred in central Illinois in the Lake Bloomington watershed. And this is an event, and this is surface flow, right? So this is surface flow. First thing I want to point out is the volume of water leaving the system, right? Secondly, I want to point out the color of that water, right? And the color of that water is an indication of sediment that's leaving the system. Sediments are attached to phosphorus, and also there's soluble nitrate and also dissolved reactive phosphorus leaving that system. So there's still a need for nutrient loss reduction strategy development, practices to be developed in field and edge of field. This second picture is just confirming this thought. This is about a 200,000 acre watershed that we monitor in northwest Indiana. And what we find here are the dynamics of nitrate loss throughout the season or throughout the year. And so we have this broken down into crop season time period and followed by the fallow period. And what you can see obviously is that during the crop season, a cash crop is the best cover crop. So a healthy cash crop is the best cover crop. It significantly reduces nitrate loss in stream, which is the combination of loss from surface and subsurface flow over time from April to October. But then after harvest, we do see a linear increase until April again when we plant the next season. And so practices need to be developed and to be enhanced and assessed and evaluated that affect this linear increase of nitrate loss on a watershed scale in the fallow period. So when you think about sustainably produced goods, or SIA, sustainably intensified agriculture, is mainly made up of two components. So the first is you want to maximize profit and you want to maximize production, okay? Second, you want to maximize profit without impacting the environment negatively. So we're looking for environmental ecosystem services from our cropping systems. You put those together and you have a sustainable system, a system that can last and feed people for generations. So I want to give some insight up front in the presentation about what we've learned from long-term projects that were funded by NREC. The first is a field scale in Lexington, Illinois. Started out and actually received funding in 2013, and then 14 we implemented, and we've been pushing forward ever since. And so what we found here is that when you have a cereal dominated cover crop, number one, impact or performance on the landscape is that cereal is able to reduce the volume of water leaving the system via subsurface drainage. So 23 to 37% reduction in the volume of water leaving the tile drain relative to the fertilized and unfertilized control. So unfertilized control, no nitrogen, but just the growth and planting of corn and soybean. Okay, so over the 10 years, we had 6 years of corn and we had 4 years of soybean, and the presence of the cereal-dominated cover crop that was planted annually resulted in a 39% reduction in our corn years, and then a 32% reduction in the soybean years. And so you can see here that kind of answers the question, should we cover crop behind both corn and soybean? Certainly, we should, and there's some reduction to be had within each of those production phases. This is an image of the cumulative loss over time. And what you can see is that the presence of the cover crop reduced nitrate loading by 42% relative to, and this 42% over a 10-year period relative to the no cover crop control. Now that gray line is an interesting one. We're in a molly soil, 3.5% organic matter on average. And so when we didn't apply nitrogen, we had crops, specifically corn, that were malnutrition, so no tugger pressure, so they couldn't put pressure on the nitrate that was being mineralized and available in the system. And so whenever you get a flush of rain, there was a lot of nitrate there to be lost. And so you got an equal amount of loss over 10 years for the no nitrogen control relative to when you added 200 pounds per acre. Very interesting there. So the next question was, does this translate to a watershed scale? So in the village of Towanda, we found 2 sub-watersheds that contributed to Money Creek. We cover cropped the southern one at about 49% of the row crop area, and from 2018 to 25, first thing I want to point out is that we saw a 42% reduction in flow-weighted nitrate concentration, and this is in subsurface flow, okay? And so also over that time period, you can see the red line representing the EPA drinking water standard of 10 ppms. We saw that the cover crop watershed never reached, the flow-weighted concentration never reached that standard, whereas where we didn't have cover crops in the control watershed, we exceeded the standard several times over the experimental period. So what are our lessons learned from these 2 long-term NREC-funded projects? So number 1, CRI is great, especially in the tile drain row crop agricultural landscape of reducing nitrate loss. The efficiency was about, on average, 42% reduction over a 10-year period. At the same time, the CRI is capturing carbon, right, photosynthetically, reducing erosion, so erosion control, and at the same time increasing the legacy pool of nitrogen within the soil, right, comparable to the reduction of nitrate loss via tile drainage. We saw limited impact on soybean yield with CRI. However, I have other studies where we have saw yield reductions, but drastic reductions with corn yield, 6 to 7%, due to nutrient immobilization. And I say nutrient because we have found out of late that sulfur is also being immobilized and affecting yield potential for corn and soybean following CRI termination. So based on this long-term study, we leveraged 3 more questions that we're going to talk about today. First, can we adjust our CRI agronomy or planting method, right, our management, planting method, seeding rate, to reduce the loss of yield for our cash crops? Secondly, is there a viable alternative or replacement for CRI before corn, speaking of overwintering legumes? And then third, can we adapt the management? Can we apply some supplemental nutrients and fertilizer to reduce the corn yield lag or soybean yield lag? So here are the 3 levers that we played with and investigated. The first is precision planting cover crops, and we'll talk about that further. The second is the inclusion of overwintering legumes, and the third is adaptive nutrient management, supplemental nitrogen and sulfur at key times during the growing season. So here's the first thought: precision planting cover crops, and then with the inclusion of overwintering legumes. And so we devised this study where we had 3 factors. The first is cover crop species, where we had Balanza clover, which is a clover that overwinters, that has the potential to overwinter. And then CRI is the Old Faithful, right, the most commonly used cover crop in the Midwest. 2 different planting methods. The first is the conventional, the second is precision, okay? And then we had N rates ranging from 0 to 250 pounds per acre in the experiment. Now, when you look to the right here, and so I call this precision planted. The other groups like Amir Singapore, he used the terminology skip row. But we found that there's some potential flexibility and advantages with this system. The first is you're only covering 50% of the area, so you can reduce your seeding rate. So then the question becomes, can we get the same performance with lower seeding rate that possibly could leverage some cost savings? Secondly, we tried to generate non-overlapping growing zones for the cover crop and the cash crop. So possibly, could we reduce an antagonistic relationship between cover crop and cash crop? And then third, in the spring, you can get some flexibility. So if you're in the spring and you want to plant, and let's say you have a legume that's not there yet, doesn't have the biomass that you need, you can plant your cash crop, let's say corn, let the legume grow, right, and then come back and terminate. And so I'll show you some of that in a bit. This is just a picture of what it kind of looked like, and this is in southern Indiana, which is comparable to like Carbondale, southern Illinois, right? And so a lot of heat units, so you get a lot more growth. And I'll show you what it looks like in central Illinois. So here's cover crop performance. Again, this is southern Indiana from 2021 to 24. You can see that planting method had no impact on cereal rye, but did have an impact on the Bonanza clover, right? Cereal rye, it's about 40 to 50% reduction in seeding rate, but yet we observed the exact same statistically similar biomass. So on average, the Bonanza clover gave us about 3,150 kilograms per hectare, whereas cereal rye gave us 2,050. And we kind of managed the cereal rye to do so because you get over 2,000 and you start running into some serious nutrient immobilization, root disease problems. Carbon, same trend, and I just threw the carbon slide in to say that these cover crops they're multifaceted and they have multiple benefits. So you are fixing nitrogen with one, scavenging nitrogen with the other, but at the same time you are photosynthetically capturing carbon from the atmosphere. Now here's one of the money slides, right? How much nitrogen is, what's the amount of nitrogen in that above ground biomass of the Bonanza clover? You can get it to grow, right? And we've been very successful in the southern part of the Midwest. It's over 100 pounds per acre of biomass, over 100 pounds per acre of nitrogen in the above ground biomass. And so the question becomes how much of that becomes a credit for the subsequently planted corn. Cereal rye, on average, took up about 45 pounds per acre. That equates to, at minimum, in that landscape, if it's tile drained, a 30% reduction in nitrate loss. But very slow return of nitrogen to the system as the cereal rye residue decomposes. Here's another interesting slide, and this is the carbon to nitrogen ratio, right? And as we suspect, when you have a legume, you have lower CNN ratio of about 13 versus cereal rye, which is on average 19, that ranged from probably about 18 to 21, okay? So the higher the CNN ratio, the slower the decomposition, the slower the release, the less utility of the nitrogen from the residue of the cover crop. So what we have here is we were trying to determine, the optimum nitrogen rate at optimum yield in this particular field. This is an average over the 4 years from 21 to 24. On the vertical axis, you have corn grain yield, and I'm sorry that it's in megagrams per hectare, but you can kind of get the gist from the morphology of the curve. On the horizontal axis, we have N rates from 0 to 300 kilograms per hectare. And so what we found was that to get cereal rye equal yield and optimum yield in the field relative to the non-cover crop control, we had to add, let's just say 40 more pounds per acre to get that done. So, and this is not anything new. There are many that have shown this. this trend. And so, but this is the conventional impact of cereal rye when corn is planted afterwards, right? So you have to add more nitrogen to get to the optimum end rate. And so when you compare that to the alternative, which is the Bonanza clover, we go in the opposite direction, right? Actually, let's just say about 30 pounds per acre less to get to the same optimum yield as the no cover crop control. So now we're moving the needle to make the yield more palatable, to make the economics more palatable. When you compare the Bonanza clover optimum agronomic rate to the cereal rye, we're talking about 70 to 73 pounds per acre less nitrogen to get to the same yield. And so this is what we wanted to determine, and we couldn't really stop here. We've done more, but for the sake of time, this is what I'm showing. We've also looked at gas emissions to determine, if there's a negative trade-off with the Bonanza clover versus the cereal rye, and so forth. And we're planning to do work to look at the leaching and to put the whole system together. So we tried this same thing in central Illinois. So big difference in the hardiness zone, big difference in the amount of growing degree days. And this is just a time lapse to kind of show you what it looks like. And this is in the spring. Of course, we planted that fall with area application with the retrofitted sprayer. We time lapse from April to May. And you can kind of see the Bonanza clover coming on. It's spotty, right? It's not even. This is what you get when you broadcast versus when you drill. And as you go forward, we planted the corn on 5/11, and then we terminated at 14 days later, 5/24, right? This was not a pretty scene. The farmer was not particularly excited about what we did, but I called him and said, hey, we need about a month more of clover growth to make this clover do anything. And he gave it to me and closed his eyes and kind of just did the work. And I know he was upset at what he was seeing, because from the road, when you compare the non-cover crop control corn versus the Bonanza clover corn, it was just drastically different, and it was visible to the eye. But what we saw is that as we moved towards side dress, we start seeing that corn that looked terrible, at about V3 and V4, we start seeing it recover. In fact, it recovered to the point that it was equal to the non-cover crop control, which was 10 to 12 bushels greater relative to both of the cereal rye treatments, even with cereal rye at a reduced rate. And so this gives potential for these types of clover, not just Bonanza clover, but crimson clover, hairy vetch, and so forth, to be used in central Illinois. Of course, you have to pull some levers and you have to adapt management, but it's possible, and the corn responds in these black, flat, poorly drained soils. So we'll shift now from thinking about nitrogen as the culprit being immobilized by cereal rye to what's happening to the sulfur. Well, when you think about it scientifically, they both have to mineralize. They both are structurally a part of the plant residue, and they have to mineralize and then become available over time for the subsequent corn to use it, right? And so our objective here was to determine if we can supplement with AMS to get a little nitrogen, and mostly we were targeting the sulfur for corn after cereal rye termination. Treatments were the control, where we had no AMS and we had no cover crop. We had AMS. The next treatment was AMS plus no cover crops, then AMS plus the cereal rye, then no AMS and cereal rye. We had about 20 pounds of sulfur applied pre-plant, okay, in a granular form. And so here's what we found. It's very interesting. This is year one. We're planning on doing this for multiple years and multiple sites, but we wanted to do some preliminary work first. What we found is that at the lower end rate, at 160 pounds per acre, there was a significant increase in corn yield where we had the supplemental AMS, 18% increase from 230 bushels per acre to 275 bushels per acre. Again, this is a molly soil, on average 3.2% organic matter, poorly drained soil. At the higher rate, we still saw an increase. It was lower, of course, and we expected that of 11% from 240 bushels to 265, right? And so the take-home message here is that possibly we were focusing too much on nitrogen, we were ignoring sulfur, and actually here we're ignoring phosphorus. They all have to mineralize and be released from the residue to be available. They all are subject to be scavenged by cereal, which causes a temporary reduction in the amount available for the corn. So at a lower rate, we supplemented with sulfur and got optimum yield that was relative to the higher rate of N. So with a little sulfur, we can save some N and possibly get the same yield and also reduce some of the environmental impacts of the higher rate of N. So we plan on digging into that further also. So what about soybean, right? So we saw sulfur have an impact on corn. What about soybean? So we want to look at supplemental increases of nitrogen and sulfur as fertility kind of pre-plant or at planting to see the impact on soybean following cereal termination. The setup here was we had 4 fertility treatments across no cover crop and then cereal systems. So we had no urea and gypsum applied, right? Those were our sulfur and nitrogen sources. And then we had the combination of urea and gypsum as the 4th fertility treatment, and we had that across with and without cover crops. And so this is what we observed. Let's start off with the no cover, right? So even when we don't have cover crops, the sulfur made a small impact on the soybean yield, plus 5.3 bushels per acre, right? But then when you add cover crops to the system, which again has the capacity to scavenge sulfur from the soil and then release it slowly or immobilize it from the carbon that's in the soil, we had a plus 13.6 bushels per acre increase where we added just the gypsum alone without the urea. And so again, here we are able to potentially close the yield gap and the yield lag, or reduce the yield lag for cash crops, right? This is soybean, but we did it for corn following cereal. So possibly we're moving in a direction where we can make adopting cover crops, this infield conservation practice, more palatable to farmers. We are advancing in our understanding of 3 major nutrients that both corn and soybean need, right? And then how cereal impacts, immobilizes, and releases the dynamics of the release and the utility of those nutrients for corn. So with that, I'm going to conclude, and then I will address any questions that we may have. So number 1, cereal-dominated mix, definitely getting reduction in nitrate loss on the field and the watershed scale. Number 2, the inclusion of winter-hardy legumes before corn gives the potential for optimum yield with lower N rates. We also saw that supplemental sulfur in the corn and soybean systems, we can't ignore sulfur. Probably can't ignore phosphorus, but we just haven't got there yet. Resulted in significant yield responses, increases, especially in the presence of cover crops, and so in the presence of cereal. So with that, I will just say thank you, and I'll address any questions that we have from the audience.
Thank you. Let's give Dr. Armstrong a hand.